All right, in this video, I'm going to discuss how you make what's called a heating or a cooling curve. And you'll see that they're relatively straightforward. After you get the hang of it, it simplifies a lot of the math involving heating and cooling curves. So they're tricky, but after you get a hang of it, it's not so bad. So the question is, how much energy is required to raise 50 grams of ice at negative 3.5 degrees Celsius to 150 degrees Celsius? And then I give you a bunch of constants: specific heat capacity of ice, specific heat capacity of water, liquid water, specific heat capacity of water vapor, the delta H of vaporization, and the delta H of fusion. The reason we need actually all of these constants eventually is because ice is undergoing isothermal and non-isothermal changes. So, at negative 3.56 degrees Celsius, what state is water in? Water is a solid. So we know that we're going to start at a solid. Again, if you don't really know how to do that, you can think about this as a number line. The freezing point of water is 0 degrees. Anything less than the freezing point is a solid. The boiling point is 100 degrees. Anything between freezing and boiling is a liquid. And then anything above the boiling is a gas. So less than 0 degrees Celsius, ice is a solid. At 150 degrees Celsius, water is a gas. So this sample is actually undergoing two phase changes. We're starting at the solid. We're undergoing the phase change to the liquid. Remember, phase changes are isothermal. 0 degree ice and 0 degree water, the only thing that's different is a phase change. Then we're also going all the way up through the phase change from liquid to gas to hotter than gas. So we're undergoing two phase changes. So it's a relatively complex problem. So we're going to start here. We're going to develop a heating curve. So we're going to start at our negative 3.56 degrees Celsius, and that is when water is a solid. We're going to raise the temperature. We're going to add in energy, okay? So we're adding in a quantity of energy. That's going to raise the temperature until we get to the freezing point, the melting point, that's the same thing, of water, which is 0 degrees. So this is solid. It's a ramp. As you add energy, the temperature increases. Now we're at a phase change. Phase changes are plateaus. This is when the solid melts and becomes a liquid. You add energy in. That's why we're going across here on the x-axis. We're adding energy in, but the temperature isn't changing. All of the energy is going for the ice to undergo the phase change from solid to liquid. That's isothermal. Energy is being added, but the temperature isn't changing until you get all the way to all of your compound is a liquid at 0 degrees. Next, we're going to add energy in. Adding energy into the liquid is going to increase the temperature of the liquid until we get to the boiling point. So that's supposed to be a straight line, but you know, just pretend that's a straight line there. This is when the ice is a liquid. Then, again, we're going to undergo a phase change. Phase changes are isothermal. You add energy in, all of that energy is going in to vaporize the sample, to make the sample go from liquid to gas. The temperature isn't changing until the entire sample undergoes a phase change from liquid to gas. Then we're ending at 150 degrees Celsius, so we're adding energy in until we get to our last part, and then along that ramp we're a gas. So it's really, really important to note the differences between ramps and plateaus. Let me change the color of that so we get plateaus. Along the ramp, energy is adding and the temperature is changing. Along a plateau, it is a phase change. So you ramp to where the phase change occurs. You ramp until the next phase change. Adding energy to a liquid sample changes the temperature. Adding energy at a phase change does not change the temperature. Okay, so now really we need to calculate things. This is where ramps versus plateaus become really important. There are 3 Qs. I'm going to call this Q1, Q2, Q3, Q4, and Q5. These are 5 different portions of energy that we're going to calculate, and when you add them all together, you'll get the total amount of energy required to raise that ice from negative 3.56 to 150. So let's talk about what's happening at Q1. Q equals MC delta T for ramps. Let me write that down. Q equals MC delta T for ramps. All right, so here is our first ramp. We're going from negative 3.56 to 0 degrees. Let me make sure I've got my math here. Here we go. So Q equals MC delta T. The amount, the mass, is 50 grams. That's in grams. The C, the specific heat capacity, we're talking about when ice is a solid. So the ice solid C is 2.11 joules per degree Kelvin or gram Celsius. We've talked about that before. Last but not least, delta T. For this particular small section, T final is 0 minus T initial is negative 3.56. So then you just add those, because subtraction of a negative, it's addition of the opposite. And so I'll let you calculate out what that is. That's how you find this small portion of energy. That's the energy it takes to go from negative 3.56 to 0. You use delta H for plateaus, and that is stoichiometry. So here we're undergoing the phase change from solid to liquid. Solid to liquid is going to use the delta H of fusion. If you look at the units for the delta H of fusion, it's in kilojoules per mole. You cannot use Q equals MC delta T. Sorry about that. You can't use Q equals MC delta T because the delta T would be 0. T final is 0. T initial is 0. But you absolutely have to have energy added in order to undergo the phase change. So we're going to use the delta H for the plateaus. We're going to use delta H of fusion for solid to liquid transitions. And it's stoichiometry. So Q2, you have 50 grams of water, which is H2O, ice. 18.02 grams of water in every 1 mole of water, that's the molar mass, times for every 1 mole of water, that is 6.02 kilojoules. And then since all of our other units are going to be in terms of joules, so that we can add them all together, 1 kilojoule is 1,000 joules. And I'll let you calculate that out. The math, doesn't really matter. But you can see we're using stoichiometry and we're using the delta H of fusion. That'll give us the amount of energy it takes to melt 50 grams of ice. Now we're on another ramp. Ramps use Q equals MC delta T. So let's talk about how we solve for Q3. I think I have enough room I'll put Q3 over here. Sorry about that. Here we go. Q3 equals M, we still have 50 grams, times the specific heat capacity. We're a liquid at this point in time, so we're going to use the specific heat capacity for liquid water, 4.184 joules per mole degree Celsius or mole Kelvin. T final is 100 degrees Celsius. T initial is 0 degrees Celsius. So 100 minus 0. And again, I'll let you calculate that out. 50 times 4.184 times 100. That'll give you the amount of energy in joules. Oh, this is joules per gram Kelvin. Oh my goodness. I got all distracted from my phone ringing. Joules per gram Kelvin. So now you can see grams cancels with grams. Degree Celsius is going to cancel with degree Kelvin there because delta is the same. You're going to be left with your answer in terms of joules. So this answer will now be in terms of joules, joules, and joules. When you're on a ramp, you use Q equals mc delta T. The C is for the phase that you're in there. Here we're on a plateau again. A plateau is a phase change. Energy is being added. All of that energy is going to vaporize the sample. The temperature doesn't change. So when you are on a plateau, you use delta H, and it's a stoichiometry equation. So for Q4, we still have 50 grams of water. There's 18.02 grams in every 1 mole of water. The specific, the delta H that we're going to use is the delta H of vaporization, because that's undergoing the phase change liquid to gas. Delta H of vaporization. For every 1 mole of water, it takes 40.7 kilojoules of energy in order to vaporize it. And then because all of the rest of our answers here are going to be in terms of joules, and we have to add them together, 1 kilojoule is 1,000 joules. Again, I'll let you calculate that out, but that's the amount of energy that it would take to just vaporize 50 grams of water to get 50 grams of water vapor. Last but not least is this last little bit of energy. That's the amount of energy it takes to take water vapor at 100 degrees Celsius and raise it to 150 degrees Celsius. When you're on a ramp, Q equals mc delta T. So Q5, that last little piece there, we still have 50 grams of water vapor. The specific heat capacity now is of the gas, the water vapor, 1.47 joules per gram degree Celsius or gram Kelvin. T final is 150. T initial is 100. And then that will give you that answer in terms of joules. So again, I'll let you calculate that off. 50 times 1.47 times 50 would give you that amount. And so then how much energy is required to raise it? The end answer is Q1 plus Q2 plus Q3 plus Q4 plus Q5. Anytime you're dealing with any problems in which you have to undergo a phase change, it is most important that you draw out the heating or cooling curve to organize when you have phase changes that are isothermal versus just adding energy into a solid or a liquid or a gas. So these ramps change the temperature as energy is added. These plateaus are isothermal. Energy is added, but the temperature doesn't change.